Okay, so let's continue where we were. Sorry for the interruption. But anyway, so the bottom line is when I look at this derivative and I have this substituted minus a half, this is the x1, then this is the term that I'm going to substitute this in. So this is then minus 2 psi, substitute in there x1 plus x2 over 2 plus, and then this term here is just, this is just a half plus psi x2. Okay. So this is what we've got. What I can see is immediately that this will cancel out. This half and half will become just 1. And what I see here is minus psi x1 and a minus psi x2. Okay, and when I look at that, I can see here's a psi x1 and here is a psi x2. So what I can see immediately here is, this psi x1 will cancel with this psi x1. And then this psi x2 will cancel with this minus psi x2. Can you see that? So this term is now taken care of, and what I'm left with is just this minus a half x1 minus a half x1 plus half x2. Okay, so that's what I have. And if I write that out a bit more neater, I can say that is essentially x2 minus x1 over 2. Okay, so that's important thing is this is a constant. Okay. And so what I've said to you, I'm not going to substitute it this into this expression. I could have done that because I want you to think about this now for just 1 second. So if the derivative dx dxi is a constant, what is the relationship between psi and x? Psi and x in the normal domain? We don't even have to substitute it into to be able to answer that question. It's going to be linear, okay? Because the derivative of something linear is a constant. I just wanted to do this on purpose just to make sure you just reflect a little bit and see that all of these things make nice sense. But more importantly, let's think about this a bit more carefully. What this is, x2 minus x1 over 2, is essentially a delta x over a delta psi. And what I mean with that is, with this special choice of x3 in the middle, this derivative, the change in x and the change in psi, is essentially given by what is the delta x, so x2 minus x1, the delta x, over the delta psi. What is the delta in the psi domain? It's 1 minus half, which is 2, which is that. So this is really just delta x over delta psi for this dx dxi. Okay, we can just think of it that in that case because of the fact that it's a constant. Okay, so this is important to understand because this allows you to very quickly be able to go and compute this. But we don't always have to go the long way. Or we can just do it systematically and make sure we code it properly in Python. And then it doesn't matter what we do because we just substitute what is the choice of x3 in there as a function of x1 and x2. Or even if you just put the physical values in, everything will work out the way. So it really is. If the Smith side is in the middle, we've got some nice property, a constant in terms of the derivative of how things change. So what this really means is if I take a delta x here, I take the same delta z there. If I take a delta x there, I will take the same distance as a delta z there. So this is really what this is telling you. Is if you take one step, if you take a step from here to here in the x world, I'm taking a step from here to here in the psi world. And that relationship is the same for any kind of scale in between. If this is obviously nonlinear, it would mean sometimes if I take a step in x, I'm taking a bigger step in psi than in other places. But that's not the case for this constant kind of case. And this hopefully will give you now a good intuition of just how x and psi is related, and that we understand this. So we'll still later on look at what happens when x3 is not in the middle, okay? And that's when I'll be talking about mesh distortion. That will do for next week. First, let's make sure we get this, what we've learned today, and start packing it into a problem. So let's apply these things, because now we essentially have a field for u, a field for w. We know how to relate this x to this psi world. We can integrate conveniently because we've mapped things from -1 to 1. We've got everything in place. If you think about it carefully, you've got everything in place to start taking that Greek form. So what I would like you to encourage, before I do it tomorrow, I would like you to try and give it a go. You know, start taking what we've learned so far and substitute it into that Greek form expression, because we have now explicit expressions for u as a so we've got u as a function of psi, we've got x as a function of psi, we've got w as a function of psi. We know how to relate. So this relates x to psi. We also essentially understand what is dx dxi, so we can relate dx's to dxi's, and just see if you can give it a go, because I'm going to then tomorrow tomorrow's lecture, we'll start tackling that problem that we did with that bar that we pull on the right hand side with the traction. Let's tackle that problem with these things that we've now derived and see what comes out of it. Okay, so this is really what I want us to explore. And once we've done that example problem, I'm going to do another example problem where we have that bar hanging on its own weight, so that we also see how do we treat body forces in this kind of finite element approach. So the first problem will be tractions applied to a structure. The second one will be body forces applied to a structure, and that should just give us a good go in terms of understanding quite well what the finite element method is all about. Okay.